Finally, let's get back to some chemistry and look at some reactions. We've been talking about all the properties of acids and bases. We've been talking about how things can be amphiprotic and act as an acid or a base. And we've also talked about how we can identify conjugate acid pairs. But it's been a while since we looked at some actual chemical reactions. And one of the things that acids do really well is they react with a number of different substances. And you need to know all the types of reactions that they can undergo. So there are general reaction types, and these will probably seem quite familiar to you because you will have done them probably in Year 9 Science. Okay, so we can have an acid and base neutralization reaction. So where an acid and base neutralize. We can react acids with metal hydroxides. We can react acids with metal carbonates or hydrogen carbonates. And we can react acids with reactive metals. These are general reaction types that acids will undergo. Okay, so we tend to look at these from the point of view of the acid rather than just looking at them from acid and base. You'll notice some of these don't necessarily specify a base in the typical way that we think of them. So if we look at this, hopefully you remember this from Year 9 when you were still writing word equations, and we have committed to our memory the idea that an acid plus a reactive metal will give salt plus hydrogen gas. An acid plus a metal hydroxide will give us salt and water. That an acid and a metal carbonate gives us salt, water, and carbon dioxide. And the same goes for acid plus metal hydrogen carbonate. The acid and metal oxides will also give us salt and water. And then an acidic non-metal oxide will give us, and will react with a base to provide salt and water. So this one's probably new, number 6. The others hopefully you are familiar with. And what you will notice is in most cases we're getting salt and water as a product. Sometimes we get a gas as a byproduct as well. But generally if we have any kind of acid base, we're getting salt plus water. So these ones for metal carbonates and things like that, hopefully you can see that with the salt and the water, we've got a neutralization reaction, but we also have a decomposition in the case of the carbonate, giving us a carbon dioxide gas being given off as well. So these are them in general, so let's start to look at them in a little bit more detail. So all of these reactions, if you remember back to when we did precipitation reactions and we said we added 2 aqueous solutions and we saw a precipitate fall out of solution, and then we could rewrite those equations in terms of what we referred to as net ionic equations, where we were only interested in the ions that were participating in the reaction. Generally, when we're talking about acid and base reactions, we often ignore the spectator ions because really we just want to see what's happening to the protons. We want to see where the proton transfer is going and what's happening. Okay, so in this same way, we get spectator ions where if they are aqueous on both sides of the equation, we can remove them because they're not doing anything that's of interest to us. So if we have a look at this equation, which is, hopefully you can see here, we have an acid plus a base, okay, which means we are forming salt plus water, so it's a neutralization reaction. HCl will completely ionize and sodium hydroxide dissociates, and we get H plus, Cl minus, Na plus, and OH minus. These are all aqueous in solution. And then if we were to write out all the things on our product side, we would have Na plus because it's a soluble salt, and Cl minus, again, both of these being aqueous, and then we would also have our liquid H2O. So if we look at these in detail, what we can see is that I have an Na plus on my right hand side and an Na plus on my left hand side. So I can actually, if my pen works and decides to let me, which it's not going to do. Okay, so let's get back. I can cross out, and you can do this on your slide, I can cross out the Na plus on the left hand side, and I can cross out the Na plus on the right hand side because they're aqueous on both sides. They haven't done anything interesting. I can also cross out the Cl minus because it's aqueous over here and aqueous on the left hand side as well. And what that will leave me with is a H plus reacting with an OH minus to form water. And generally all neutralization reactions will simplify to this kind of reaction, which is given here. This is our net ionic equation. H plus plus OH minus goes to H2O. The proton is donated it's accepted onto the OH minus and forms H2O. So typical acid-base reactions will have very similar ionic equations usually. So let's have a look at neutralization reactions in detail. Again, this is our acid plus base gives salt plus water, and hopefully you remember from our energetics unit that neutralization reactions are exothermic. So our solution will actually heat up when we start to have a neutralization reaction. We use ionic equations to show the reactions because that allows us to show just the movement of protons. So in this case, this is our full balanced equation, and our net ionic equation will be the H plus OH minus goes to H2O, and we would put our states in as well. If we look at the case of acids plus metal carbonates, in this case, what we're going to do is we've got an acid plus a metal carbonate. So metal, any sodium, potassium, any kind of metal, with carbonate, our CO3 2- anion. So when we have that, such as sodium carbonate, when these two react, we get H2O plus NaCl plus CO2 gas. And this would be seen as bubbles coming up out of solution. If we were to write the ionic equation, we can see here that we've got Cl minus on the right hand, Cl on the right hand side that's aqueous, and Na plus on the right hand side which is aqueous, which means that I can actually cross out my Na, I can cross out my Cl, and I'm going to be left with this being removed as well. So what I'm going to get is 2H plus aqueous is going to react with carbonate, aqueous, to give me, and I'm going to have to go down to the second line here, H2O liquid plus CO2 gas. And these ones stay in my equation because they're not aqueous on both sides. I've got a liquid and a gas, and gases and liquids always stay in my net ionic equations. The test to confirm this, we can actually do a test in the lab, which you will do, to confirm whether or not the gas being produced is carbon dioxide. So we could go, oh, it's carbon dioxide, but we can't really check it unless we do some tests on it. And what we can do is we can actually take any gas that we produce, like in this image over here, and bubble it through a solution of calcium hydroxide, which is what we call lime water. And what that will do is this CO2 will react with the lime water, and it forms an insoluble precipitate, which turns the solution cloudy. If this was hydrogen gas or nitrogen or any other gas, it wouldn't have this reaction. It would just stay clear. But if it's CO2, it will start to turn cloudy. So in that case, we can use the lime water test as a test in the lab to confirm the identity of the gas that is produced. I suggest that you look up the equation for the lime water test and bring it to class with you to show me that you've done it. Okay, but we want the test for the lime water test. So a little bit of a Google search and you should find that one, no problem. So the other one that we looked at was acids plus reactive metals. So that was acids plus metal carbonates giving CO2 plus our salt. In this case now we're taking acid plus reactive metal and we're reacting it to get salt and hydrogen gas. This works really well with metals like magnesium or zinc or something like this. So the equation that we've got here is zinc plus 2HCl goes to zinc chloride plus H2 gas. I want you to pause the video now and have a go at writing the ionic equation. Once you're done, restart the video and I'll go through the answer with you. Okay, hopefully you've done the equation and you came up with zinc solid. It's solid and going to aqueous, so it's going to stay in our equation. Plus 2, well, we've got Cl over here and Cl over here. They're both aqueous, so we're going to lose our Cl minus. So that'll leave me with 2H plus aqueous is now going to go to Zn, and this is Cl minus. So I've got 2 of those, so this must be Zn2 plus aqueous plus H2 gas. Okay, so this would be my net ionic equation. The aqueous ions that are aqueous on both sides have been removed, and we can see that it's the hydrogens that are being donated, the protons being donated, reacting with the zinc that forms Zn2 plus and H2 gas. Now I want you to think about this. Do you think this is an acid-base reaction according to the Bronsted-Lowry definition? Yes or no? Write down your answer and I'll check with you in class. So the way we can test whether or not the gas that we're seeing in this, so if we put the magnesium metal or the zinc metal into a test tube full of hydrochloric acid, we'll see bubbles of gas being formed. But again, unless we test that gas, we can't be certain what it is. In this case, you may remember doing this experiment, we can collect the gas. We collect the gas in an upturned test tube, and if we put a match or a glowing wooden splinter into it, that gas will combust really quickly and formed a large pop sound, and we call this the hydrogen pop test. So if it was any other gas, again, we wouldn't see that same kind of reaction. So what you're going to do now is pause the video, open up your slides that you have copies of, and I want you to have a go at writing each of the following chemical reactions. You're going to write the balanced equation for it, and then you're going to write the net ionic equation for it as well, so that you get a bit of practice writing those, and we will check the answers the next time that I see you.